M&M's claims each package of milk chocolate M&M's should contain 24% blue, 14% brown, 16% green, 20% orange, 13% red, and 13% yellow. Do the counts from our bag fit this distribution model? Well, our bag, which we'll assume contains a random sample of M&M's, has the following counts: 55 blue, 20 brown, 35 green, 49 orange, 18 red, and 23 yellows. So, in order to check this and see if what we observe in our current bag, these 55, 20, 35, and so on, if that matches the given percentages that we expect to see, we're going to use our chi-squared goodness of fit test. So, going through these first steps, we have to define our hypotheses. And so, just like we've done before, we have a null hypothesis, H0, and our alternative hypothesis, HA. For these hypotheses, we can start off by putting them either in words or just listing them out. Since we have a lot of different proportions here that we want and not just wanting them to be equal, it makes sense to just write them all out individually. So as you can see, the proportion of blue is expected to be 24%. The proportion of brown is 14%. So we just go through and write each one of these out. But to save time for the alternative, it makes sense to just write at least one proportion is incorrect, because all we need is one of them to be wrong, and the entire thing will be wrong. For step 2, we're just going to write the name of the test so that way we know what we're doing. It's the chi-squared goodness of fit test. And so to check those requirements or assumptions and conditions that we need to satisfy, we have our IRL conditions. For independence, we check is 5%, is n less than 5% of our population. Well, if we find the sum of all these values here, it looks like we have about 200 M&Ms. So I think it's reasonable to assume that having 200 M&Ms is less than 5% of all M&Ms. So we'll assume it's independence. Also, we're making the assumption that the bag itself can be considered a random sample of all the M&Ms. Finally, for the large enough, we need to find the expected counts, the expected frequency for these counts. So one way we could do that is we can go through one by one. So for example, if I have 200 M&Ms in a bag and we expect 24% of them to be blue, then we can go and find the expected count of all the blues by just taking 0.24 times 200. However, we won't spend the time doing this because StatCrunch will do this for us. StatCrunch will give this value of 48. So what we do need to check though is once we finish the StatCrunch parts, then we can actually just check, are each of these expected counts greater than 5? Well, this first one is, but we'll let StatCrunch figure out the rest of them. So let's see how we can use StatCrunch to do this type of problem. The way we enter this into StatCrunch is we put it in two different columns. One column we have our expected, and we can put either the expected counts or the expected percentages. For the second column, though, we have our observations. And here, we want to make sure that these are always counts, not percentages. So our observed values have to always be counts. And now, where we are going to go is under Stat. We'll see that there's actually an option here that's called goodness of fit, and one of these is the chi-squared goodness of fit test. So we'll select that one. It'll ask us where did we put our observed values. It's under, I titled it OBS for observed. And the expected frequencies I put under EXP. Now you'll notice that if we wanted them all equal, you actually have this option also, and we could have just left off this. So for example, the two examples that Khan did in his Khan Academy videos, we can just select those rather than typing in each individual proportion. In any case, we have the individual proportions, so we'll select that column. And all we need to do now is do compute. And there we go. So you'll notice it gives us here all the observed counts which we did. Not only that, but it calculated the expected counts for us here. So that 48 that we calculated by hand, it does that for us. And we find that the expected counts for the next column, which is brown, which is 28, then 32, and so on. So going back to step 3, we see that each of these values are greater than 5 for the expected counts. so our expected counts are large enough, and we can use this result. So finally, moving on to step 4, which is what are those calculations? Well, here we go. These are the things that we want. We have our degrees of freedom is 5, which is the number of categories minus 1. So we have 6 categories, 6 colors minus 1 gives us 5 degrees of freedom, but it tells you that here. The chi-squared value, so this is our test statistic. So if we went through this entire calculation of finding the observed minus expected squared over expected, and then adding them all together, then it would give us this chi-squared value here. And then finally, our p-value is 0.1345. So as always, these are the main two things, the chi-squared value, the test statistic, and our p-value are the two things we want to report. So on our step 4, let's report those. We have chi-squared is equal to, looks like about 8.42. And our p-value looks like it's about 0.1345. And there we go. There's our step 4. Oops. So finally, let's work on step 5, which is our conclusion. And the way we conclude this is the same way we've done this for all of the other ones. All we're going to say is, since the p-value is greater than 0.05, oops, we fail to reject our null hypothesis. So we don't have enough evidence. There is insufficient evidence to show any of the reported proportions are incorrect.